Shibashis Guha will present Mean-payoff adversarial games. Okay. Yeah, so we are already running 15 minutes late. So I hope you guys can delay your lunch. And Shibashis, over to you.
Yeah, thanks, Ashutosh. So I'm going to talk about Mean-payoff adversarial Stackelberg games. And this talk is going to be based on the following two papers. So this one, the first one is the adversarial Stackelberg value in quantitative games, which appeared in ICALP last year. And at the end, I will briefly touch upon this second paper, which is about fragility and robustness in mean-payoff games, mean-payoff adversarial Stackelberg games, which has recently been accepted Conquer. Yeah, so I would also like to mention the authors of this paper. The first paper is by Emmanuel Filio, Raffaele Gentilini, and Jean-François Rasca. And the second one is a paper that I co-authored with Mrudula Balachandar and Jean-François Rasca. Okay, so what are Stackelberg games? So in this kind of games, we have a leader and a follower. In general, there can be multiple followers as well. And they capture somehow strategic interaction among rational agents. So the players here are rational, so they have their own objectives that they would like to satisfy. And this is like the game proceeds kind of sequentially, in the sense that the leader announces her strategy and the follower would announce his response, maybe a best response to the leader's strategy. And we can just have a quick look of this kind of games with the help of this kind of bimatrix setup. So consider that these are that in the red you have the leaders. Sorry.
Shibashis, can you make it full screen?
Okay, I thought I made it full screen, but somehow it's not visible. Sorry. Okay. So let me try again. I'll just stop sharing and see if okay, let me share. How about now?
Yeah, that's good. Yeah,
that's good. Yeah.
Okay. Okay. Thanks. Okay. So yeah, I think oops. Yeah. Okay. So I would like to illustrate this idea of the Stackelberg games with the help of these bimatrix games first. So first here we consider the profiles. By profile, I mean essentially these cells where there is a strategy which is chosen by the leader and where is a strategy which is chosen by the follower. And we consider those profiles or cells where the follower doesn't have any motivation to deviate. So for example, we are interested in these profiles, like one where both the players have chosen their first strategies and the one in which both of them have chosen their second strategy. So why they're interesting? Because if we consider this one, so is my pointer visible? Is my pointer?
Yes.
Okay, thanks. So if I consider this one, for example, where the leader and the follower, both of them have chosen their second, this strategy too, then the payoff that the follower gets is 1, and there is no there is no real motivation or advantage of deviating to this particular strategy of the follower. And similarly, if I consider this one, the follower would not prefer to to move to this particular strategy because, okay, the payoff that the follower gets becomes 0 here. So we are interested, first of all, in those strategies or those profiles where the follower doesn't have any unilateral beneficial deviation. And among those ones, the leader is going to choose the one which gives her the maximum payoff. So for example, here between these two, where the follower cannot deviate or follower would not like to deviate, the one that gives the leader a higher payoff is this one, because here the leader is getting 2, whereas here the leader is getting 1. Okay, so the leader will be interested in choosing this particular profile, I mean, okay. So now also we would like to note that this particular profile here, it is not really a Nash equilibrium. So the only Nash equilibrium that we have here is this one. Okay, so because okay, neither the leader can improve by a unilateral deviation, nor the follower can improve. But here this is not Nash equilibrium, because indeed the leader can increase her payoff. So sometimes it can indeed happen that these leaders, this specific kind of leader strategies, which give or these profiles that give the leader the maximum payoff, they may yield a higher payoff for the leader. Okay, so so again, the leader suggests a strategy and the follower would respond with the best response. That is the idea in this kind of Stackelberg games. And now we are not really looking at these bimatrix games, but we are looking at mean payoff games which are infinite games that are played on a finite arena. So in Supratik's talk today in the morning, we looked at, we got some idea of this finite arena, but I'm still going to talk a little more on these things. So essentially in this finite arena, there are vertices, there are edges, and the vertices are partitioned into the leader vertices and the follower vertices. So these are the follower vertices, which I draw with the help of the squares, and the leader vertices are essentially the circles. And in every round, so as I said that the vertices are partitioned, so it's like, so the leader owns this vertex, for example, the follower owns these two vertices. And in every round, what happens, so when I say that in every round, initially the game starts from an initial vertex. We can consider as if there is a token in the initial vertex, and this vertex is owned by the follower in this particular example. So whoever owns this particular vertex where the token lies at some point in time or at some round would actually choose which outgoing edge to choose, or essentially it's equivalent to saying what is the successor vertex that this player is going to choose. So for example, initially we have the token here. In this particular round, the follower is going to choose whether to take this edge, this outgoing edge, or to take this outgoing edge. So if the follower chooses this outgoing edge, then in that case, the token remains here. And if the follower chooses this outgoing edge, the token goes to this vertex. And next, in the next round, what happens is, if it happens that the follower chooses this edge and the token comes here, then now it's the leader's responsibility. Why? Because leader is the owner of this vertex. So it's the leader's responsibility in the next round of the game to choose an outgoing edge. So it may be possible that the leader chooses this edge, and again in the next round, again the token stays here, and the leader is going to again in the third round going to choose another edge. Let's say this time the leader chooses this particular edge, and the game continues like this. Okay, so now in every round, whenever an edge is taken, there is a payoff. There is a payoff for the leader, which is given by which is essentially defined by the edge that is chosen. So there is a payoff for the leader on the edge. There is also a payoff for the follower on the edge. And this game continues ad infinitum. And essentially what we have is an infinite path. We have an infinite path, and in each of the edges of this infinite path, there is a payoff that the leader gets, and there is also a payoff that the follower gets. And what we are interested in is the mean payoff objective. So it's like the long run objective. So you essentially have an infinite path, and we are interested in the long run average objective or mean payoff objective of the players. Now this kind of things have essentially been studied. But okay, maybe before I continue with the next slide, I would like to know if there are any questions with the setting and
Yes,
if so.
Shibashis,
Yes.
just one question. So I don't understand the leader-follower terminology here. So isn't it? It looks like a multi-objective mean payoff game. There are two players, and so
No, not really. So essentially, like if you see that in the beginning, it's like so it goes in sequence. So the leader suggests something, and the follower would have to provide the best response. So follower is, I mean, unless and until the follower has something which is much better. I mean, so as long as the leader suggests something and the follower is going to provide a best response, and and uh, and the
No,
game
no.
proceeds in this way. Yeah.
So this is in the biometrics game that you're talking about, right?
Yes. Yes.
No, in the graph game, it looks turn-based. Like there is a token, and then whoever owns that token announces the move, right? Like at V naught, only follower moves the token, right?
Sorry. It's
No, no. So in the graph game,
yeah.
like uh,
Yes.
uh, like when at V naught, for example, it is followers position. So follower announces, I mean, decides whether to take A or B.
Right, right. So yeah, so I think I'll come to some examples. Maybe that will be
Okay.
clear. So there will be, indeed, there are
I
some strategies of the leader based on which the follower would like to would like to do something.
see. I see. Okay.
Yeah,
Okay.
yeah, sure.
Yeah.
Thanks.
Thanks. Yeah.
Okay. So now this kind of setting has been studied in the in the context of rationals. I mean, it's actually this kind of work is it's a contribution to the rational synthesis framework, which is modeled as a non-zero sum game graph where you can consider the leader to be like a program, and it has an environment where the environment, it can consist of one or several rational agents which also have their own goals. And this has been essentially studied for qualitative omega regular objectives. So in this paper by, so one paper by Fishman, Kupferman, and Lustig, and in the other one by Kupferman, Pirelli, and Vardy. Okay, so they have been studied for omega regular objectives, which are qualitative objectives. And here we are interested in quantitative mean payoff objectives. Okay, so so I spoke about the mean payoff game. I spoke about the Stackelberg games, and there is also one more element in the title of the talk, which is called mean payoff adversarial Stackelberg games. Now, what is meant by this adversarial thing? So it essentially denotes that the follower here is adversarial. Okay, so the follower is here is adversarial. So consider that here the leader, suppose, has two possible strategies. So I'm going to define formally what a strategy means. Essentially, the leader can either choose this edge or the leader can choose this edge. Now, if the leader chooses, for example, this edge from V0 to V1, then the follower, being adversarial, not only, so first the follower would like to maximize the payoff that he can obtain. And then if he has multiple best responses, he would also like to minimize the payoff of the leader. So this is what is meant by the follower being adversarial. So for example, here, if the leader chooses this particular edge, then what happens is that the follower would like to choose this one, because among all the payoffs are essentially the same for the follower, that he gets 10 in each of the cases, but choosing this one is going to minimize the payoff of the leader. So the follower being adversarial is going to choose this edge. Now, if the leader chooses this one, then similarly, the leader is going to get 3. And for the other one, the leader is going to 1. So the leader is going to maximize also her payoff, knowing in fact that the follower is adversarial. She would choose this particular edge. Okay, so the mean payoff value that that essentially the leader that she gets, it's 3, and this is called the adversarial Stackelberg value of this game. Okay, so and what we would like to argue that one could also consider a cooperative follower, in which essentially what the follower would do, along with maximizing his payoff, he would also like to see that if the leader also gets a better payoff. Now the adversarial thing makes more sense because here we do not have much assumption on the behavior of the environment, apart from the fact that we consider that the follower is rational. Okay, so the rationality of the follower is the only hypothesis we make on the behavior of the follower, and the leader should be prepared to face any of the responses of the follower. So that is the idea. Okay, and what are strategies? So strategies are essentially like given a finite path that ending in a leader vertex. So we are talking about leader strategies. So it is the choice of the successor vertex. So this is the leader strategy, and similarly one could also define follower strategies. So you have a finite path that ends in a follower vertex. Then what is the successor vertex that the follower is going to choose? So this is how the follower strategies are going to be defined in general. But one could also think of memoryless strategies where the edge that is going to be chosen, it depends solely on the current vertex and not on the history. Okay, so this is what we have, and then I talked about what the adversarial Stackelberg value means. So essentially, like if we consider that there is a strategy sigma 0 of player 0 or leader, then there are multiple possible best responses maybe, and the adversarial follower would choose the one which is going to also among the best responses, the one which is going to minimize the payoff of the leader. Okay, so this is the adversarial Stackelberg value corresponding to this strategy sigma 0 of the leader, and then the adversarial Stackelberg value from the vertex is the supremum over all the strategies, all the leader strategies that one gets. Okay, so now as we already saw that the adversarial Stackelberg value for this particular game can be 3 because the leader chooses this one and the follower is going to choose this one because this minimizes the value of the leader, and that what we get is that the adversarial Stackelberg value to be 3. Okay. Now there is a technical problem in the definition, so which is the following. So we were talking about the that we define the adversarial Stackelberg value as one in which the follower is going to choose a best response that minimizes the value of the leader. But it may happen that in these kind of games, the best responses may not even exist. Okay, so here is a simple example. So for example, the leader strategy is the following, that at some point of time, the follower would actually like to choose this edge and maybe visit these edges here, because here you get higher payoff, like you get 10 and 5. I mean, follower gets so much. And whereas here the follower gets like 0. So the follower would actually like to choose this edge and come in this part of the game graph. Now the leader makes a strategy. Well, if the follower chooses this self loop k times, then the leader will also choose this k times before sending it here, and then it will come back and it will repeat like this. So if it is like if the follower chooses something like akb, so that means like you repeat here k times, take this loop k times, and then you choose this edge, then the leader will choose this edge k times and then choose the d action, and then it will return here, like it will come back here. Now, as we see that as k increases, so as k increases, the follower is going to get higher and higher payoff. The follower is going to higher and higher payoff. But now you consider any particular value, say which is, so the best response that the follower, the best that possibly the follower could have achieved, which is something like a 10 minus epsilon for epsilon to be strictly positive, but the follower is never able to achieve the value of the best response, which is 10. So for every epsilon where epsilon for positive epsilon, if you have if you consider 10 minus epsilon, then the follower can have can go as close as possible to 10 minus epsilon, but he can never achieve the exact value of 10. Okay, so this is essentially, it illustrates that the best responses may not exist in this kind of games.
Sorry, question, Shibashis,
Yeah.
sorry. So I had a question in the definition of ASV. Can you go one,
Yeah.
2 slides before?
Yeah.
So here, when you say mean payoff L of outcome of sigma naught, sigma 1, it is looking at the first coordinate of the...
Sure. Thanks. So
Right.
I sort of, so when I say this L means essentially the mean payoff of the leader. Yeah. Thanks for asking that.
That means
So
the first coordinate.
the first coordinate. So the ASV is the value that the leader gets. So you have the outcome, and in the outcome, which is like a path, you have, of course, both the coordinates. But then when I'm saying that this mean payoff L, so we are looking at the first coordinate. So this is the value that the leader gets.
So in this definition, the second coordinate doesn't come into picture at all.
In this definition, the second coordinate, it's not like the second coordinate does not come in the picture. So you have this sigma 1. So essentially, like you consider the whole, you consider the path pi, and then you consider like among the best responses of player 1, among the best responses of player 1, which is the one that minimizes the payoff of the leader.
I see.
Okay, so the sigma 1 are in the best responses, and you get the outcome by choosing this sigma. I mean, of course, sigma 0 has been chosen by leader, and you choose sigma 1, which is among the best responses. And then you get like the mean payoff of the leader, but then the follower is going to choose the one among those best responses, which gives the minimum or the infimum over all such mean payoffs that the leader gets.
In the best response computation, you use the second coordinate.
Yes, I mean, exactly. Right.
Okay.
Yeah.
Right. Thanks.
Yeah. So, so as I said, that best response may never exist because, like you can never achieve the, essentially this player 1 or follower, he does not have a best response, right? So you only have epsilon based responses where epsilon is strictly positive and can be smaller and smaller. This is the idea. Whereas, as I said, that epsilon based responses for any epsilon value, one can show in general that any strictly positive, any positive epsilon, that epsilon based responses always exist. Okay. So now we reach this technical problem is that, if we define this in this manner, then in fact this set may be empty, and this is not really interesting. So how are we going to define the value of ASV in that case, the adversarial Stackelberg value? So hence we consider like epsilon based responses, and we want to have the epsilon as small as possible. So this way, since we want the epsilon to be as small as possible, we have this part here. We want the epsilon to be greater than 0, but the value of the epsilon should be as small as possible. And this is how this is just a technical modification in the definition. And what is an epsilon based response? An epsilon based response of follower to a leader strategy is one which is at most epsilon worse than every other response of follower. Okay. So this is how we define the adversarial Stackelberg value. Okay. And the second result that I'm going to talk about is this adversarial Stackelberg value also may not be achievable. Okay. So why is it so? So again, remember that the adversarial Stackelberg value is the value of the leader. It's the value of the leader. So suppose this is the initial vertex of the game. What can happen is that this player who is the follower can choose this edge. And if chooses this edge, then the leader is going to get 0, which is of course not interesting for the leader. But now if the leader can actually ensure that the follower gets something which is slightly greater than 1, right? If the follower gets slightly greater than 1, then by doing something here, then the follower might be interested in taking this edge rather than taking this edge, because the follower is going to get higher payoff. But in that case, the leader has to ensure, leader has to choose a strategy such that the follower gets something better. So now what the leader can do here is that every time it comes with very small frequency, the leader can actually choose this edge. Okay, and the frequency can be smaller and smaller, but it cannot be 0 because if it becomes 0, then the follower is going to choose this edge, and the leader is going to get a value of 0. So the adversarial Stackelberg value, which is the supremum over all the strategies. And what is the strategy of the leader here? Is to take this edge, how many number of times maybe. So this can be different strategies. And this should be with frequencies lesser and lesser. This should be different strategies that the leader would like to have. And but yeah, the supremum value that the leader can get is of course 1. But this is not achievable. So the leader doesn't have any strategy which can give her the value of exactly 1. But for any epsilon, the leader can get something which is greater than 1 minus epsilon. Okay, so no strategy for leader is there which can give her a mean payoff of 1 for herself. Okay, so the ASV value in fact may not be also achievable. So now we look at the third problem, which is about, so how am I doing on time?
Few minutes left.
Okay, okay, so I'll
maybe 4 or 5 minutes. Yeah.
Okay, so I'll try to wrap up. So the threshold problem, it asks that given a rational threshold C, is the adversarial Stackelberg value greater than this value C? So the threshold problem essentially depends on the idea of a witness. And what is a witness? A witness is a path pi. And if we ask this question whether the adversarial Stackelberg value is greater than C, it's a path pi for which the mean payoff of pi is C prime comma D, where C prime is strictly greater than C. And there is also another condition which I'm going to describe, which says that pi, this path pi, does not, so pi is an infinite path and it does not cross a CD bad vertex. So what is meant by CD bad vertex? So for which we consider this set, and this set essentially includes those pairs of points C comma D, they can be real values, such that from vertex V, so this set is with respect to a particular vertex V, such that from this vertex V, player 1 does not have a strategy that ensures that leader gets a payoff less than equal to C and follower gets a payoff greater than equal to D. Okay, so path pi will have multiple vertices, and it's a witness such that from each of these vertices, there should not, I mean, none of the vertices should be something like this, that the follower can ensure a payoff for the leader which is less than equal to C, and the and for himself the payoff is greater than equal to D. Okay, so so these vertices are good vertices. Okay, from which the follower cannot have anything of this sort. So so the path pi should not see any of the bad vertices. Okay, okay. So this is the notion of the witness, and what one can show is that the adversarial Stackelberg value is greater than C if and only if there exists such a witness for ASV adversarial Stackelberg value being greater than C. Okay, and we can add more actually. So we can also show that we not only have a witness, but we can also have a witness which is regular. And what is a regular witness? So it's a path which is of the form u dot v omega. And this v, so the u part here consists of just one acyclic, finite acyclic path p, pi1, and the v has just two cycles, L1 and L2, and they're connected by two finite acyclic plays, which are pi2 and pi3. So you not only have a witness, but you can also have a regular witness. And this also leads to an NP membership for the threshold problem. It's not very trivial, so I'm not going to discuss more on this because of the interest in time. But given the fact that you have such a regular witness, and I mean the difficult part comes here, that one would like to show that in fact that this regular witness also should not cross a CD bad vertex. For all the vertices that appear, they are not CD bad. Okay, so this gives the NP membership for the threshold problem, and one can show that if we restrict ourselves to memoryless strategies, then the threshold problem also becomes NP hard. So for memoryless strategies, we get
1 minute left.
Okay.
1 to 2 minutes left.
Okay, sure. So then the final problem that I'm going to look at, it's about the computation of the adversarial Stackelberg value. So the adversarial Stackelberg value, how we compute it, it also uses the notion of a witness, and I'll possibly skip some of the details. And it shows that the witness can be encoded with the help of first order theory of reals over addition. And yeah, and effectively this can effectively be computed. And what we could also show that one can express them with the help of linear programs, where the objective is to maximize C, which gives an exp time algorithm. So now I'll just briefly touch upon the second part. I'll just take one or couple of minutes max. So now what we could also show that this adversarial Stackelberg value, this is fragile. So what does it mean to say that it's fragile? So it's fragile for perturbation of weights. So we are looking at quantitative objectives, and for example, if the weights change here, it may be possible that the strategy that you had for computing the adversarial Stackelberg value does no longer work in the presence of the perturbation of the weights. So for example, So for example, I don't see this. Okay. Okay. So for example, what I was, I possibly lost some slides. Okay. So what I'm trying to say, if this, for example, changes from 10 to let's say 9.45, this goes to 9 point, and this changes from 9 to 9.55 under some, let's say, a perturbation of maximum allowed perturbation of 0.6. So in that case, what happens is, yeah. So what happens is in that case that that the ASV that you would get, if this becomes say less than, so if this becomes, let's say 9.55, this becomes 9.45, then the follower would like to choose this one, and then the value that you get, the leader gets under such perturbation becomes 0. So the strategy that the leader has is not robust against perturbation. In that case, actually the leader could have used a strategy which is like this one. Okay, and also if the follower is not optimal, but if the follower is happy with playing suboptimal responses, then one can show that again the strategy that the leader would choose for the adversarial Stackelberg value, they are not quite robust. They are again like fragile. So what happens that, but okay, I'd just like to mention that if you consider whereas zero-sum games instead of non-zero-sum games, they are always robust against perturbations or epsilon-based responses. So this is very generic to, in general, like non-zero-sum games, this kind of behavior which can appear. Okay, and so we suggest something called a different solution concept, which is ASV epsilon. Here the idea is that the follower would fix an epsilon, and or we fix an epsilon and we look at epsilon based responses, and this turns out to be robust against the perturbations of the games, and also it turns out to be robust against the suboptimal responses of player one. So when it comes to the notion of robustness, then the adversarial Stackelberg value, this solution concept is not robust, but we suggest the notion of ASV epsilon. So yeah. So I think I'll stop here. Yeah. Sure.
Yeah. Can you just?
Yeah. Sure.
It's up to you.
So this was my last slide anyway.
Yeah. Just go ahead, finish it.
Yeah, all I wanted to say is that there are two things. I mean, it's like the ASV epsilon, the threshold problem we can also compute in exp time, and given such a threshold C, one can also compute the largest epsilon that is allowed such that this ASV epsilon is greater than C in exp time. And one small difference with the ASV is that ASV epsilon one can show to be always achievable. Okay, so sorry for taking more time and possibly rushing over the last part, but I'm done. Thanks.
Yeah. Any questions?
So maybe I can ask a quick question. Sorry, like I'm still wondering about these two coordinates. I'm sorry. Is that like if both of, I mean, in every tuple, If the value is the same, then does it boil down to a normal mean payoff game?
So in every tuple, the value is the same. So you mean
Or,
that?
like it's one or one minus one, I don't know. Like
so this becomes like a zero-sum game, right? Yeah.
No.
So
Like no. I'm not fully sure. Like no. So
So
the
if
second player wants to maximize her objective,
the second player
and
wants to maximize
knowing
his
this,
own object.
so okay. So if both of them are the same value, then it's just the normal mean payoff game, is it?
Yeah, like if you have, for example, 1 minus 1, then it becomes like a standard mean payoff game, which is like a zero-sum game. So I mean, maybe I can just add a comment here that if you consider the epsilon, like I talked about this, I was talking about all these epsilon. So what is the epsilon here? So epsilon is, the thing is that player 1 is satisfied with an epsilon based response. So I'm happy with a suboptimal response. Now, if I say that this epsilon is like, there is no bound on the epsilon can be arbitrarily large, right? Then also it boils down to kind of standard mean payoff game, because in that case, the player 1 will always be interested in minimizing the payoff of player 0. So I'm happy with my epsilon based response, but my epsilon is too large. Then what I will be doing is that I'm happy with any of my responses, and I'm in addition going to minimize the payoff of the leader. So then it boils down to, like with arbitrary large epsilon, it boils down to zero-sum case.
I see. Okay, I see.
Yeah.
Okay, yeah. Thanks.
Yeah, thanks, Srivatsan. So
Any other questions?
okay, maybe I'll stop sharing my screen.